Hi class, this is Mr. Krieger. I'm going to be attempting to teach you through the YouTube channel. This is both my geometry class alone and also the class with Miss Stillman. We're going to continue. We're doing Unit 8, Part 1, Lesson 8, which is in the booklet that you have. It's the last lesson in the unit called Midsegments of a Triangle. So why don't you find that lesson? You could pause the video at any time. So if you need to find something or try something, it'll give you an opportunity. So this is our first problem. I've already drawn a triangle here. But again, pause the video if you need time to read the question. But what's happening here is this triangle ABC is being mapped to triangle DEF after a line reflection. So imagine there was a reflection over the line, let's say this line, and it became A went to D, B went to E, and C went to F. And that was followed by a translation which mapped DEF to XYZ. So D became X, E became Y, and F became Z. And they want to know the relationship between the original triangle ABC and XYZ. So these are the choices. Why don't you pause the video and see if you could figure it out. But I'm going to continue to answer the question. Well, what we know is that this sequence of transformations is a sequence of rigid motions. So we definitely know that triangles are congruent. So we could eliminate choice 3 and we can eliminate choice 4. The thing is, are these triangles also similar? And the fact of the matter is, the triangles are similar because of the following fact. A dilation is a similarity transformation, and a dilation with a scale factor of 1 is a dilation as well. We know that when you do a dilation, the triangles will be similar. So here what we're learning is that congruent triangles are also similar, but similar triangles do not need to be congruent. So it goes one way, but not the other way. All right? So let's move on to the next part, which is really the heart of the lesson, because this lesson is midsegments of a triangle. So now we're going to define what a midsegment of a triangle is. So you could try to fill in these blanks, but I'll fill them in if after you pause it. Here's what we know. A midsegment is a line segment of a triangle that connects the midpoints of two sides. So if you see this diagram here, this piece, DE, is the midsegment. There are two things that we know. And again, keep in mind that this is a midpoint and this is a midpoint. These are the two facts about midsegment. A midsegment is literally half the length of the parallel side. Not the two sides that it touches, but the third side that it's parallel to. It's literally half of this. Also, we know that the midsegment is parallel to this side. Those are two key facts. So let's see if you can solve this problem. If AB is 15, how big do you think DE is? Pause the video if you want to try it. Well, we know it has to be half of the third side, so it has to be 7.5. In problem number 3, we know that DE is 10. You could try to find the missing side by pausing the video. The answer would be 20, because this is double the midsegment. And now we have an algebraic problem to try, in which we have that AC is 3x minus 15 and DE is 6. Well, we need a way to solve this. Since we know the midsegment is literally half of the segment it's parallel to, this is a reasonable formula to use. It is 2 times the small piece, which is the midsegment, is equal to the large. So therefore, 2 times the small, sorry, my pen is running out of ink, is equal to the large, which in this case is 3x minus 15. Let me go to another pen. You know how to solve this. This becomes 12 equals 3x minus 15. We get 3x equals 27. Divide by 3 and x equals 9. Let's see if that's what they're asking for. Yes, they asked what the value of x was. X is 9, choice 3. Okay, move on to the next page. Sorry, we gotta find the next page. Here we go. Question number 5. So here we have a more complex problem, a little bit more complex. Here's what we see. In the triangle below, DE, EF, and DF are all midsegments. Here's what they give us in addition. AB, that whole thing is 20. BC, this whole side is 17. And AC, this whole side is 21. And we need to find the length of each of the midsegments. So look very carefully here. This one should be obvious. Again, you can try to fill these in on your own by pausing the video, but let's see. This should be obvious. Half of 21 is 10.5. What might not be so obvious is what these sides are. This is half of this side. Remember, it's a side that it's parallel to, so it's got to be half of that. Half of 17 is 8.5. And this is parallel to that side, so it has to be half of the side it's parallel to. This must be 10. Now, sometimes on the regions, they actually ask you to, let's say, find the perimeter of this triangle. Well, once you find each midsegment, you could then just add them together and find the values. So just, by the way, I'll just fill in these values here. DE is 10.5, EF is 10, and DF is 8.5. Now, this is a more complex problem. Why don't you see if you could solve it? Let me read it to you and you can try it. In the diagram below, triangle ABC, these are midsegments. It says DE is 9, BC, which is this side, is 17, and it wants the perimeter of quadrilateral FDEC. Now, FDEC is definitely a parallelogram because we know this is parallel to the side that it's a midsegment of. It's the midsegment of these two sides. It's parallel to this side. And this is parallel to this side, so this figure has to be a parallelogram. It wants to know the perimeter of that figure. Well, we know that this is half of the side that it's parallel to. This has got to be 18, but that's irrelevant. Each of these are 9 since that's a midpoint. Now, if this is 17, the midsegment has to be half of that 8.5. This is the midpoint of BC, so this is 8.5. So the perimeter will be the sum of all the circled values, which is just going to be 9 plus 9 plus 8.5 plus 8.5. This is 18 and 17, which is 35. Okay? Now, going back to the same diagram, if the measure of angle DEC is 105, what are the following angle measures? ECF. Well, it's a parallelogram in there. These are supplementary. This must be 75. CFD. CFD angles opposite each other in a parallelogram are equal. And DFA, well, if this angle is 105 because opposite angles are equal, there are two supplementary angles here, so this one must be 75 degrees. Okay, last page. Actually, let's see where it is. Okay, so here's one additional thing that we're going to learn today, and that is going back to our volumes. We have a cone here, and in this particular case, the cone is filled up with a liquid. What shape does the water make inside the cone? So here we have a cone, and we filled it up with water. I'll shade it in green, pretend that's water. We want to figure out what shape that is. Well, that shape in there is a miniature cone. What do you notice about the shapes created by the radius and the waterline? The shape created by the radius and the waterline is that it is a right triangle. And what we're going to do here is we're going to use the fact that this triangle here and this triangle here are similar to each other to help us solve a volume question. So let's take a look at this problem here. Before we continue on, let me just grab one thing. Okay. The radius and the radius of the original cone and the height of the cone made a right triangle. Inside here, the water line and the height of the smaller cone also makes a right triangle, and because this angle is in both triangles, and because parallel lines, these lines have to be parallel, have corresponding congruent angles, this big triangle and this small triangle must be similar, okay? These are two similar triangles because they have two right angles, and they have a reflexive angle at the vertex here. Okay, so let's try to use that to solve a problem here. The cone below has a radius of 4 inches, that's this radius, the large radius, and a height of 12. The cone is filled with water to a height of 5 centimeters. What's the volume of the water inside the cone? Well, what we really need to know is the radius and height of the little cone. We know the height of the little cone is 5. What we need to do is find the missing radius. I'll call it r. That's what we need to know before we actually use the volume formula for a cone to figure out the volume of water in here. So what we see is these triangles are similar. I'll draw them separately. We have the larger triangle with a radius of 4, or a leg here of 4, and a leg here of 12. And we have the smaller triangle with this leg of 5, and this side we'll just call it r. Since they're similar, we could make a proportion to find r. 12 is to 5 as 4 is to r. Cross multiply, and we get r is 20/12, which actually reduces to 5/3. Now you know, you go to your volume formula, and now you can substitute the values for the smaller cone, which is radius of 5/3, don't forget to square that, height of 5, and if you put this value into your calculator, you get 14.5444 repeating, which to answer the question to the nearest tenth, the volume of the water inside the big cone, which is its small cone, is 14.5 cubic centimeters to the nearest tenth. Okay guys, please try homework 8, which is review sheet number 1, okay, for homework tonight. And again, you can always rewind this video to try to figure out what I did if I was moving too fast. And you could always leave questions in the comments section of the video. All right, have a good night.